Okay, let's get going. I'm trying something new here. Oh, I'm so excited. I think it's going to work just fine. I'm back in my little area. Feel so comfortable up here. We're going to talk about alternating series today. Alternating series, you're going to find out real quick. We can do something really rad with alternating series that we can't do with any other kind of series. So again, we need a healthy respect for infinity. We need to be able to do limits at infinity, and again, we need to be able to tell if something is bigger or smaller than something else. All right. So far we've only done done series that have all been positive. Right. That has been one feature of all of the series tests that we've applied so far. All of the series have been positive terms. But what happens if they alternate, right? So clearly, if they're all negative, you can just factor out a negative and they're all positive again. So what about if some of them are positive and some of them are negative? We did see that with geometric series, but it was okay because as long as the common ratio was between -1 and +1, that was allowed. But now we ramp up into bigger like not necessarily things that are geometric. So here are two series. This one on the left, you may recognize the values: 1, a half, a third, a fourth, a fifth, etc. That's the harmonic series. Now this is the alternating harmonic series. You see every other term in red is negative. What's that do? That's going to be a head scratcher. And then there's other ones that don't really alternate every other term. There's like some negatives in a row and then some positives in a row, and there's not necessarily an alternating pattern. Case in point, Hector here. He's got like 3 negatives in a row and then a few positives in a row. Not necessarily an alternating series, but again, one that we're going to talk about in a little bit. All right. So what think about what's happening here with an alternating series. Since the terms are bouncing back and forth, positive to negative, I like to work out. I like to, jump around. Maybe you do too. Think about an alternating series as jumping back and forth from one foot to the other. Jump in the positive direction, jump in the negative direction. Jump in the positive direction, jump in the negative direction, back and forth. So the goal of the workout is to eventually get our feet to settle onto one spot, right? To converge to one spot. So we're going to kind of do this workout to kind of make the analogy to a convergent alternating series. So maybe you want to pause the video and start jumping. I don't know. We'll see. So maybe here is one scheme that you could take where your jumps are always the same size. There's a workout that I do where I'm always jumping the same distance back and forth. Well, is that meaning that we're converging to one spot in the on the floor? No, clearly not. We're just jumping the same amount. Well, that means the jumps can't stay the same size. So the jumps could get bigger. So if the jumps get bigger, then obviously that's going to be harder and harder to perform. But I'm not converging onto one spot in the center. So that means the jumps can't stay the same size. They can't be getting bigger. They have to be getting smaller. All right. So here's another scheme. Maybe the jumps are getting smaller, but they're getting smaller, but never smaller than a certain measurable amount. So yeah, I'm jumping back and forth, but if my jumps kind of settle on this distance here, then I kind of end up back to the first scheme where I'm jumping the same distance back and forth and not settling onto one spot. So what that means is that the jump sizes have to be getting close to 0. So ultimately, this little analogy to jumping back and forth tells us about the convergence of an alternating series. For an alternating series, right here we have the alternator, -1 to the n. That's the thing that's bouncing back and forth, positive to negative. A sub n is just the sequence of values. For this alternating series to converge, the values of a sub n have to be decreasing. They've got to be getting smaller, and their limit at infinity has to be 0. So it's kind of a combination of a couple things, like the nth term has to be 0 for an alternating series. And really, if you can seal that deal, if you can say that the limit of the sequence is 0, you've basically kind of captured the entirety of the alternating series test. So if you've identified a series as alternating, and you can show that the limit of the sequence is 0, you're done. That's basically proving that that's convergence. So let's talk about that harmonic series for a second. We know the harmonic series diverges, but let's look at the alternating harmonic series. So the terms again bounce back and forth between positive and negative. Now what's happening is we want to look at the part that doesn't alternate. We want to look at just the sequence of values. Just set aside the positive, negative for a minute. We know it's switching back and forth. But look at the values of 1 over n. Now 1 over n, one way to show it would be to say that is the n plus 1th term, which is 1 over n plus 1, is it smaller than 1 over n, than the nth term? Now generically that's how we would show that it's getting smaller, but I think you can reason out that a half and a third and a fourth and a fifth, those are getting smaller. So cha-ching! That first criteria is met. Is the limit as a sub n, as n goes to infinity, of 1 over n, is it 0? Well, of course it is. So cha-ching on that one too. And what does that mean about this alternating series? It means that the alternating harmonic series converges. Okay. So we have the harmonic diverging, but the alternating harmonic converging. More on that if you stay tuned. All right, let's take a look at another one. Here is another alternating series. I know that because I get this little negative 1 to the n critter. That's telling me that it's alternating. But then the numerical part is n plus 3 over 3n plus 1. So we want to see if this thing converges. So we got to ask the question, is it getting smaller and is it trending to 0? So yes, the terms get smaller. Look at that craziness. I think if you probably wrote it out, the terms, and like just understood that the denominator is being multiplied by 3 and the top is just being added. So it's kind of clear that the denominator is getting bigger faster than the numerator. So maybe you could make that argument not so convoluted as this over here. Don't think it's got to be that complicated every single time. So the numbers are getting smaller. That's good. Is the limit of the numbers 0? No. It's 1/3. Well, that's that idea that I'm jumping back and forth, but I'm not getting any smaller than 1/3. So I'm essentially jumping back and forth between two spots on the floor rather than getting settled in the middle. So that series diverges. Oh, hey, that's what I wrote. Let's look at another one. Here is a third example for a alternating series. We know this is alternating because we get this negative 1 to the n critter right there. Now this one's going to be fun. We're going to see this one later. Let's prove that it converges or diverges first. So do the terms get smaller? And is the limit of the number part 0? Well, yeah, those numbers are getting really small, right? N factorial is a super fast grower. So those numbers are getting really tiny, really quickly. So cha-ching on that one. Is the limit of the numerical part 0? You bet your bottom dollar it is. So cha-ching on that one too. So that means, holy cow, that means that series converges. Okay, so that's cool. This is cooler. This is even cooler. Okay, dig this. So something that we can do with an alternating series is estimate its value. So back to the two questions from the very beginning of this unit. Does the series converge? More interestingly, what does it converge to? Now I talked about in that lesson how we're going to spend most of the time talking about whether the series converges or not necessarily coming up with the value that it converges to. But alternating series are a little bit different because we can estimate the value of alternating series to as exact as we want to get. Now, we may not be able to get the exact value, but we will be able to estimate the value really closely. Okay, and we'll know with confidence how close we actually are. So don't think we're finding the sum. We're going to be able to estimate the sum within a tolerance that we know is exact. Not exact, but within a certain tolerance. So think about the jumping, right? In the jumping, I have to, every time I make a jump, I jump over the actual sum. And I'll refer to the actual sum as the Holy Grail sum, right? The search for the Holy Grail. Like, what is the actual sum? Nobody knows. But every time I make a jump, I have to jump over that sum, right? So something about the distance between where I stop jumping and the actual sum, I'll know that. Like, I know if I end on a positive jump, the sum was behind. If I end on a negative jump, I know the actual sum is ahead. So the alternating series, I can keep jumping, and the more I jump, the more I shrink a window where that actual sum needs to live. Let me show you a picture of what I mean. So if I keep jumping, right? Jump, green is adding, red is subtract, forward, backward. So I add, I subtract, I add, and I keep jumping, and I stop right here. Okay, if I stop right there, the Holy Grail, the distance between the Holy Grail, real deal sum, and this approximation, that is the exact error. That is right there, that's the exact error. And I don't know that because I don't know the actual sum. Remember that. Now, since I don't know that, is there maybe a restriction that I can, is there something that I know is bigger than that exact error? Yes, there is. Because if I made one more jump, if you make one more jump, this yellow arrow here, that jump is bigger because you have to jump over the Holy Grail sum. That jump is bigger than the exact error up here. Now, I know that distance, right, because it's just the next term. So here is a little callback to Indiana Jones. Thank you. See, if you haven't watched that movie, pause this. Go watch Indiana Jones and the Last Crusade, and then pick up. Okay, did you watch it? It was great, right? You have chosen wisely. You know what else is a wise decision? Subscribing to my YouTube channel and hitting the subscribe button and the notification bell and all that other stuff. All right, here's what the alternating series remainder says. It says for any alternating series that converges, the sum of the first n terms differs from the actual sum, s, by less than the first unused term of that series. So this difference here, s minus s sub n, right, that is the exact error. We call that the remainder. So that r sub n is the remainder after the first n items. That error is always less than that next term that you would use, the n plus 1th term. So that's rad, isn't it? That's completely rad. All right, so in this example, we're going to look at this series and see if we can do some stuff with it.